right, everybody's approved of the recording of the video since I'm the only one on the meeting. I think I've approved of it. All right, so number 30 is where we left off yesterday. You should have had C for that. All right. So now we're working on this decomposition one. So see if you can get the answer to this guy. I'm going to try to do my little snipping thing here where I can get enough of this to be able to write on here. I think this is, I was talking about this one and then we kind of ran out of time. I didn't get it finished. Okay, so when you think you got the answer, put your slip up on the back side of your Chromebook. All right. Well, Miss Woods, congratulations. You got that one right. The answer is indeed B. Okay, now let's talk about why. If this is 1 atm, okay, and we have 1 mole of material here. Now this said to completion. Okay, that's the key word here. Okay, they're not saying that this is going to establish equilibrium. They're saying that all of this is getting converted into all of this. Okay, you see that? That's where they got most of you. Okay, they're saying to completion. So all of this goes over here. So this is 1 mole of material, and that's 1 atm. How many moles of material will we have over here? How many moles of material will we have over here? 2. So this would be 2 atm. 1 atm here plus 1 atm here equals 2 atm. Got it? They're sneaky. I know, they're a little sneaky. Ooh. All right, next one. Next page, number 32. So which of the statements about the Kp value, equilibrium for the constant, is correct? See if you can figure out what the Kp value, if it should be equal to 1 or north or south of 1. Figure that out. Well, ice table. Remember our ice tables? Did you set up an ice table for this guy? Did you? I got 1 answer for this guy. I got 2 answers, 3. Okay, everybody's B. Everybody says B. That's good because the answer is B. Let's talk about why. Okay, this guy, and initially we're going to go from here. We're going to minus x. Here we're going to plus an x and plus an x. Remember, we would need to use our stoichiometric coefficients, but in this case they're all 1, so everything's x here. Adding here, or subtracting here and adding here. Whew. So this becomes x, this becomes x, and this becomes 1 minus x. What did these equal? 1.4 ATM. So if we want to solve for x now, 1x minus x plus x would be 1 plus x, right? Equals 1.4. So x would equal what?
0.4.
Yeah, 0.4 ATM. Okay. So then if I take 0.4 times 0.4 over 1 minus 0.4 is 0.6. Okay. This answer, this guy times this guy would be 0.16, right? Over 0.6. So 16 over 6. What's that answer be? Yeah. Okay. Because you could think of it as like 1.6 over 6 if you wanted to move the decimal point so your brain can think without that decimal point there. Okay. It's going to be less than 1, isn't it? And so because of that, you know, you don't have to know what it is. You just have to know that it's this. Does that make sense? So you remember how you solve those guys? All right. See what you can do for 33. Put your answer up on your Chromebook when you think you got it. We got 2 B's and 2 C's. The B's have it. Okay. So the reason why B is preferred over C, it was good that you recognized that, yeah, this jacked up here. So that was good. I'm glad to see that. Okay. So this guy, this would have said, hey, you know, we didn't have anything going on before this until we added that. So that guy's out. This one, though, notice that we're still going to have more going this direction than we did initially. Okay, so here's where it was. When it levels off again, it's going to be higher than that one. This one would have been lower. And that added material in is going to change that rate of reaction. Okay. All right, let's keep going here. We got the next one here. See what you can do for this guy. It's number 34.
Chit-chat with you about it.
You ready? Anybody going to give us a go? Come on. Don't you leave any of these questions on that AP exam blank. You at least give them a guess, okay? Close, but no cigar. The rest of you not even in the ballpark. Okay. Love you guys. Love you. Love you. Love you. But don't you leave a single question undone, okay? Don't ever do that. All right. How much heat is released or absorbed when 0.05 moles of Cl2 is formed? Okay? So Cl2 here is a reactant. If Cl2 is formed, it's not going to be a reactant anymore. It would be a, and what would happen to this number? Exactly. So because of that, we are going to get rid of the top two here, okay? Because it's not going to be released. Okay, do you see how I can easily eliminate those two? Now, I need to figure out which one of these it's going to be. And I don't want to have to do math on this. That's just frustrating, okay? But I have, I can see here, where did I go with this? 0.05 moles. Yeah, so this is already a half of an amount, right? So then this is a half of amount and it's equal to this. This is half of a mole-ish. Okay, I know it's not half of a mole technically, but when we're talking in these terms, this is doubling that amount. Do you see that? So we don't really have to do any math here. We just have to reason through this. Since this is at a half and that's at a half, then that means that we're going to go with C. That makes sense?
Okay, just out of curiosity,
yeah.
What does the RxM stand for?
Reaction. Mole of reaction. So if we go through this whole thing and we have 1 mole of this and a half mole of this and we make a mole of this, that's how much heat is going to be released. Mole of reaction. Sometimes you don't have a whole mole of reaction, so you're not going to generate that much heat or absorb that much heat. Okay? If this value is negative, it's released. If this value is positive, then it's going to be absorbed. Okay? All right. What remains in the reaction vessel after equal masses of K and Cl have reacted to form this stuff? So equal masses. This is a stoichiometry question, y'all. Number 35. What's your answer? I got one up. Anybody else want to give it a go? Don't you leave a question blank. I got another one up. Okay, that says cheating. Looking over it. Well, you can't do that on the exam. Don't you do that on the exam. Okay, so got everybody's answers up. When we look at this, if what I did for this was I went and I picked 40 grams. Why did I pick 40 grams?
I'm guessing that's one of their...
That's the molar mass of K. Okay, so if I divide this by the molar mass, that's going to give me 1 mole of this material, right? Here, I did 40 grams of this. I'm going to divide that by 71. Okay, so 4 and 7, that's probably around 0.6 or so. All right, I'm just doing that math in my mind. I don't know for sure that that's what it is because I don't have a calculator that I can lean on. But I know it's greater than 0.5. You can tell that, right? Because if it was 0.5, this would be 3.5 up here, or 35 over 70. Okay, so I know that it's greater than that. So then, if I've done that math, that means if I've got equal masses here, that means that this guy is going to be my limiting reactant because this is in a 1 to 0.5 or a 2 to 1 ratio. I'm going to use up 2 of these for every one of these I use up. So if I use all of this up, I'm still going to have some of this left over, and I will have made some of that. But I'm not going to have any of this left. Does that make sense? So the answer for that one is indeed C. All right, 36. Which of the values for the process in the table is or are less than 0, which indicates an exothermic process? So which of these, or all, how many of these, what are they? What are these are exothermic or releases energy? Get your answer up for that one and we will talk about it. All right, so got all B's and an A. So let's talk about this. If we go from a solid to a gas, is that going to take energy?
Yes.
Yes, so that guy is definitely endothermic. Okay. If I rip off an electron, is that endothermic or exothermic? Endothermic. If I rip a molecule apart into 2 different parts, is that endothermic or exothermic? Endo. If I put an electron back on something, is that endo or exo? I'm putting this electron back on. It's just getting attracted. It's going ploop, like a magnet. That's exothermic. And here I've got a positive and a negative getting attracted to one another. Endothermic or exothermic? Exo. Okay. So Y and Z are exothermic. So the correct answer for that one is letter B as in boy. All right, try the next one. B, you got one answer up, or is that left over from last time? Reset. Ready? Oh, Austin's the odd man out again. But that's okay, because none of you are right. Love you guys. Okay, so, yeah. So, let me ask you why they're focusing, wait a minute. So when I do this, when I look at this one, I only focus on these two equations. Why? Why would I only look at those two equations to figure this guy out? Look at your answers. Look at the answer options. Why am I only looking at these two things? Did you see the answers to the questions?
Yes.
Those are the only ones that have that.
Around 37.
Oh. You're mean. You're mean. Okay, then I don't know what the answer I gave you to that one. Who had A? Oh, good. You got that right. All right. So, okay, here. Let's talk about this one now. So the reaction is favorable and driven only by enthalpy. What is happening in terms of entropy here? Is my entropy increasing in this or decreasing in this reaction?
Increasing?
They almost say the same because you have a solid on one side and a solid on the other.
Right, but look at my moles. I've got one here and I've got a half here. So I've gone from 1.5 moles to, and I've gone from 2 things down to 1, right? So I have decreased my entropy, yet the reaction is still running. Okay, it's exothermic, so you know it's thermodynamically favorable. It's favorable. It's driven by enthalpy only. The entropy, in order for the entropy to run this, we would have had to increase our entropy, and we decreased it because things, remember, favor disorder. Things favor positive, and I mean, look at my room, for God's sakes. I mean, you know, my entropy has increased to a point where I can barely like function.
So you can tell when I'm behind the school because my room falls apart.
Yep, exactly. Okay, so that's why we know that it's favorable because we have a negative delta H here. Okay. And we know that it went to, if it goes to completion, it's favorable. Okay. We know that we have a negative delta H, so that tells us as well. So the reaction is favorable. So we either want A or C. And we know now why entropy doesn't play a part in it. All right, so 38. Let's try 38 now and try to figure out what this is. First of all, getting back to my point that I was trying to make, you're only going to focus on these 2 lines of the reaction because they have brought you into that. They've told you from these options that that's the case. Okay? So that helps you out a little bit, maybe. We've got one answer. Anybody else going to be brave? Oh, good. Everybody has a consensus, and that consensus is correct. So good job. And the answer is indeed C. okay? So when we look at that reaction, okay, in order for, how do I do this? Cl2 plus 2 electrons. So Cl2 plus 2 electrons. So we'd have to reverse this guy, right? Cl2 plus 2 electrons. So this guy we would have to double. And this guy,
I think both of the equations stay the same. You just have to double the one and then combine them.
yeah, that's it. That's the problem is I'm trying to look too many, I don't have enough screens going here. I need another screen or two. So Cl2 here leads us to 2 of these. Yep, and then that's going to give off 2 of those. So you're going to double this guy because you're going to have 2 of these feeding in. So we'd have to double this. So we're going to add x plus 2y, and that gives us our answer. Okay. All right, I'm done confusing myself right for that second anyway. All right, see if you can figure out 39 and get your answer up. That doesn't involve any math, so that you should be able to get a fairly quick, well, I guess it does involve a little bit of math. I guess it does. I'll shut up. You're going to need your periodic table for that one probably. Ready? Well, yeah, put it there or take your cover off. I don't know. Such a whiner. All right, so the answer to this guy is A. Did you get A? Nope. Okay, let's talk about Y. Okay, what does this come down to? What do we need to be looking at for this in order to figure out when they're going to meet? What's going to be the determining factor in that? My hint was you need your periodic table. Molecular mass, how heavy these things are, all right? I'm not getting around a track faster than somebody that's lighter than me, most likely, okay? So we're going to look at the molecular mass for this. For HCl, my HCl here, hydrogen is 1, and this is 35.5, so we're just going to call this 36 just to make life easier, okay? Here, I've got carbon is 12. I have hydrogen, I've got 5 of those, so that's 17. And a nitrogen at 14, 7, 8, 9, 10, 11, 31. So 36 and 31. Here, I've already calculated this one. This is 36. Here, this is 14, and 3 is 17. Okay? These are pretty close to one another. These are not. So that's why B's out. HBr, we've already calculated this guy here. So he's 31. He is 17. Well, bromine is a big brother. So he's 80. So we already know this is 81 and 81. Okay? Let's see how to figure that out. So which one of these are obviously lopsided. So they're gone. So that leaves us with A. Good? So that's how we tell that one. Okay. Try 40. This goes back to Okay, where you at here? You got your answer up for me? All right, let's talk about this guy then. Okay, so is phosphorus going to have mobile positive charges? Why? What's going to happen to phosphorus? When phosphorus is sitting here, what's phosphorus going to want to do to become stable? Gain electrons, right? So he's going to want to gain 3 electrons, which is going to give him a -3 charge. So that he's going to introduce negative charges, isn't he? So B's out. GE atoms have more electrons than SI. They do, but how many valence electrons versus the other? Well, this guy is going to have +4, or have 4 valence electrons, and this guy has 4, so they're pretty much equal. That's out. And GE atoms are not ever going to be smaller than SI. Why? Because as we go down the periodic table, what happens to our atomic radius? It gets bigger. So that would be out. That leaves A as our option. All right, try 41. If you guys think I'm upset about you getting these wrong, I'm not. That's why I want to go through these, because I need you to start thinking the way they think. Okay, so don't think that I'm mad at you or upset at you or angry with you. This is what my expectation was, just this. Okay, so don't be freaking out that you're getting everything wrong, because once we get started with this review and get going with it, that will change. Okay, just give me time to work some of my magic. And the C's have it. Good job. Okay, so yes. So A, more energy is required to make N2 vibrate than I. Nope, that's not going to be it. We're not able to, that's not going to explain why we're seeing one versus the other. Okay. We can't, the UV light, the N2 absorbs it, but visible light, but not visible light. I2 will absorb both the visible and the UV. So giving N2, like it doesn't, it works for I2, and I2 is bigger, so A's out. B, the energy is required to remove an electron. Removing an electron is not what gets something to light up or not. Remember, we're just transitioning. We're just moving it from one level to the next, and it's dropping down. When it drops down, that's when it's giving off that energy that you're able to see as either visible or UV light. Okay, So C, visible light does not produce transitions between the levels in N2. It doesn't allow it to get to that level, okay? But it does produce those in I2. And then the molecular mass is irrelevant here as well, okay? So try 42. Oh, this is an alloy question. Interstitial and substitutional alloys we talked about. Austin, you are good. All right, the C's have it. Very good. Okay, so if we look at Cu, Cu has two common oxidation states, but Ag doesn't. That's not going to help us understand why we're having, why it's getting stronger and harder. Okay. So the the gold and copper versus this is stronger than this guy. So why? Okay. So two oxidation states here doesn't matter. That's irrelevant. Okay. The oxidation states are going to make a difference. The Cu has a higher melting point than Au, but Ag has a lower melting point than Au. I could see where that might, end up.
Accepted.
Yeah, I mean, I could see where you might pick that one, but the best explanation, okay, is going to be this displacement. This is one of those substitutional alloys where it's going in, and this is our gold atoms, okay? Our copper is a much smaller size, and that's what they're trying to show you here, that copper is much smaller than the gold, and that copper is going to fill in these. This is called an interstitial alloy, and they're going to fill in those interstices. And when it fills in those interstices, that tends to make the stuff much harder and stronger. That's where your steel is created, where they take iron and then they take carbon and they fill in the iron atoms with the carbon in here. That's where your stainless steel comes into place. And that's why they're able to build big buildings and all of that stuff. So that's the best one to choose in that option. Okay. Let's try 43. See where we come. Oh, this takes us back to the first few months of school. Remember these guys? why is it harder to remove? It says here, the photospectrum shows the energy required to remove a 1s electron. So we're removing a 1s electron from here, from a nitrogen, to form an oxygen atom. Which of the following best accounts for the peak in the upper spectrum? Why is it harder to remove a 1s electron from oxygen versus nitrogen? Why is this electron held on tighter? First of all, how do I know it is? Well, because of the values down here. So it's harder to remove this guy versus this guy, okay? So nitrogen will have a half-filled P sublevel. Well, if he has a half-filled P sublevel, okay, this is what he looks like. Oxygen looks like this guy, okay? If we tried to remove one electron from oxygen here, or from the thing, have we changed anything about the inside? This has 8 protons, this has 7 protons. What's holding that 1s electron? This is my second energy level here. What's holding that 1s electron on here? What's holding him into place? The protons. Have I changed anything here about the protons? No. So A's out. B, electron-electron repulsion in the oxygen. So yeah, you're going to have a little repulsion here, but they're saying that it's holding on to this electron tighter. So that guy's out. Electrons in the P sublevel of the oxygen atom provide more shielding. No, they don't provide more shielding. The shielding would have to come from another layer here, and that doesn't exist. So D is the only thing that's our option here. Nitrogen has a smaller, it has fewer things holding that electron, that S electron in. And so this has more. This is going to hold on to this guy tighter. He's staying in tighter, and that explains this.
You want to keep the
Yep, keep them. We'll keep going with this. If I don't finish tomorrow, I doubt I will at this rate. So I only got through 13 questions today. All right, bye guys.
Third, what's good? What? Steph taking third test guy. Third test? Yeah, I'm already like behind the school. I